Okay, so today we're going to talk about interpolation. I'm going to make this as big as possible. So I will do this. It's going to work. Okay. All right. We had a question on the test that actually used this first term here. So we're going to talk about interpolation today. And talking about interpolation, there are two different categories that most interpolation techniques fall into. Spatial interpolation is basically the process, should have had a slide on this, right? It's basically the process of making a continuous surface from point observations of a real-life continuous surface. So if we have a continuous surface, like what am I talking about there? What might be some continuous surface that exists in the real world? Yeah, I mean the interstate. Okay.
Elevation.
Yeah, elevation is probably the example that's most tangible that we can actually see. If you go outside, you notice that you go up and down in elevation, right? But there are other what we usually refer to as statistical surfaces out there that aren't necessarily tangible, but they do exist. One of them might be temperature, precipitation. These are surfaces that we've been using, right? We haven't necessarily thought about how this data gets created, but do we know the elevation everywhere? Do we have that knowledge that we can just make a map of that? Well, we can find it out, but we don't actually know it every single place. And also, when it rains, we don't measure precipitation everywhere. You know, we know we can derive it from some sources. We can look at cloud tops and kind of make a guess at how much water fell. But more commonly, we measure precipitation by rain gauges, which occur at a point location, right? We might be concerned with pollution in a water body like Bay St. Louis or Biloxi Bay, and we might be trying to model that. Well, we go out there and we take measurements. We sample the water, and we find out how many parts per million there was of a particular pollutant. Or we might be interested in finding out the same type of information from soils. So we go out and we take a soil sample and we figure out how much lead or how much iron, different chemicals are in it, and then how do we turn that into a map if we just have points? Well, that's what today is all about. This spatial interpolation is deriving a surface from point data, from point observations. And the first one that you probably actually have been introduced to in the introductory GIS course, I don't know if it's how deep you get into it, but you may have learned about deterministic methods for interpolation, like IDW stands for inverse distance weighting, and trend is a trend surface. So there are a couple different things. We'll go over them and look at the formulas for how they're created. We're also going to spend time today talking about geostatistical methods. Specifically, when we apply geostatistical methods to creating surfaces, we call that kriging in GIS literature and geospatial literature. So geostatistics, remember, is all about looking at spatial autocorrelation. And so if we try to include the spatial autocorrelation of the observations that we have in predicting the new observations, that process is called kriging. And kriging shares a lot of similarities with inverse distance weighting. we're basically, in a nutshell, in a very simplified way, we're basically modifying the weights according to measures of spatial autocorrelation. One of the advantages of doing geostatistics kriging is that the techniques do not simply output a statistical surface, they also output a uncertainty surface. So usually you can get two different surfaces. You get your prediction surface, which tells you, what your predicted value, and you get an uncertainty surface, which tells you how good the predictions are in a certain area, or how much you might be off by. So we're going to talk about those two today. So, like I said, we're talking about these things, these surfaces that exist in nature, or they're virtual surfaces, but we can think of them as a continuous surface. It's a good candidate for interpolation if it exists everywhere, but we only have observations at certain XY locations. So topographic elevation is one of the most obvious examples, but anything that's numerically measured and that varies continuously over space can be measured in this way. Even some things you wouldn't think about right off, like population density. Population density is the amount of people per square unit of land. And we can use point observations of this value to create a continuous surface. Basically, if it's interval or ratio data, meaning that it's a quantity that represents an actual amount of that value. And that's different than, let me turn these guys down. That's different than like land cover. That's different than like land cover, where we might use a number to represent, one might represent urban and two would represent rural. Okay, but a value of 2 in that case doesn't mean that there's twice as much of anything than the 1. But interpolation is useful for variables where a 1 means a certain amount of that value, and a 2 represents twice as much of that value than a 1. Okay. With elevation, you might argue, well, what does 1 elevation mean? It represents 1 foot above some datum. So it doesn't have a real 0 mark, except for an arbitrary one that we determined was a 0 line. It's not like 0 elevation means there's no elevation. It just means that you're at the datum. You're at the 0 mark. That's what we usually refer to as interval data, and ratio data has a real 0 mark. All right, so when we do interpolate a surface, there are a few different ways that we can do this, and we went over a little bit when we were talking about elevation, the difference between raster grids and TINs, or triangulated irregular networks. We're going to focus today mostly on raster grids, okay? But now that we're talking about interpolation, another format to store a continuous surface in is actually referred to as an isorhythm. Okay, that is like a contour line. Contours are the term we specifically apply to elevation data set. But in general, let's say the contours represented temperature or precipitation, then we wouldn't call them contours. There's actually specific terms for all different types of these types of lines. Okay. There are other formats that we could store our data in. One is referred to as a lattice. Okay, but we're mainly going to focus on a raster grid. But realize there are tools for converting back and forth between each of these. So we can convert from a tin to a raster, or from a raster to a tin. We can convert from contours back to a raster, and vice versa. there are tools in there for doing this. But our products are going to, our examples and our efforts are going to take and produce a raster grid from points, which is usually what we mean by spatial interpolation. What happened?
That's me. I was just trying to change the camera.
Oh, okay.
Yeah.
Hey, Kevin. Thanks. Yes. Thanks for getting that up on the screen, Kevin. Does it look a little clearer up there? It looks like it does.
Yeah, it looks good.
Okay. Thank you. Thank you very much. All right. So we basically have we can basically work with two different types of continuous data that if we want to turn them into a continuous surface. One is that we have actual point observations of a geographic variable, some geographic entity. We have point observations. An example of this would be weather stations. At every weather station, we're not counting up temperatures. We have a value that represents temperature. We may have another value that represents humidity. We may have another value that represents the precipitation for the last 24 hours. These are point locations that have observations. The other example was the one I did before. If we went out and we took some point observations of some continuous variable. The other type of data that's often turned into a continuous surface is referred to as punctiform data. And that is when we have observations of specific individuals. So that might be people, or it might represent, bird nests or turtle nests or some other thing that we're trying to come up with. We're trying to make a continuous surface to give us a value per unit of land. We talked about this a little bit already, but this is the processing of punctiform data will basically be a specific type of kernel that we refer to as density estimation. So density estimation, the second thing that's listed there, it creates a field from discrete objects. So we have points that represent the location of things that we're trying to create a surface of, that we use density estimation. If we're trying to do the first category here, temperature data or numerical data, we use spatial interpolation. Thanks, Kevin. Do you have to do anything special to switch it back when I teach from up there again, or?
No, I'll be back this afternoon. Philip's going to be here this afternoon and hopefully get the system actually working properly.
Okay. Well, I'm not going to teach up there until next week, but.
Okay.
But I think we have a couple more classes. Thanks a lot.
Okay.
You can zoom back out and we can see you now.
Okay, I'll do that. I mean, if you want to.
Yeah.
All right. There we go. Okay, so we've got, if we've got our discrete objects, like I said before, if these represent people or, in this class, I forget whether, because in the other class I talk a little bit about the Dr. Snow's cholera study from way back a long time ago. Was that this class or? Okay.
Yes, we talked about it.
We talked about it in this class?
The very beginning.
The very beginning, yeah. So we might be looking at the density cases of a disease. So in other words, every observation in that example would be if we had a bunch of people living in a city and we basically geocoded or found a way to, we're not going to cover geocoding in this class, but we found a way to reference the location of where they were, the people that had cholera, then we could use that as input to what we're talking about here. We also can technically do the same thing with linear features and polygons, although this is usually applied to points. So we might get the density of roads in an area, or even the density of polygon features. Polygons present a little bit of a problem because they're already polygons, and we're really counting everything. You'll see that on the next slide. Yeah. You could do it with polygons, but the idea would be that typically your search area here is much larger than the average size of a polygon. So you're basically treating polygons as if they're a single location. Right? So yeah, this is the basic process of creating a surface from punctiform data, where we have our point data, and we then pass a moving window, and this moving window is very similar to the moving windows we've talked about before, only it doesn't operate on a raster data set. It operates and looks for observations within a certain range of the center of every cell. So it's still going row by row, the center of every cell, and it's looking out at a certain distance around that. So you specify that. So in this case, it might be 5 meters. So what it's doing is counting up, creates a density surface where it counts up all of the observations inside of that circle. Now, ArcGIS does this in 2 different ways, and most software packages do. One is that you can request the raw density surface, and the other one is that it will actually, you can specify that you don't want the raw density surface, you want the density surface divided by the area within the circle. So if that area, if like I said, if that's 5 meters, what's the area of that circle? Well, we don't have to calculate it up, but it's pi r squared, right? Is the formula for, so we take 5, multiply it by 5 squared, which would be 25, multiplied by pi. That's the area of that circle, so it'd be 2 divided by that value. ArcGIS refers to this as kernel density, and we cover this a little bit in more detail in the vector GIS class. But this is interesting because today's lecture kind of it straddles the boundary between vector GIS, because usually these observations are vector GIS, but we're creating a surface, so we're turning them into raster layers. We've got our density surface there on the right. Now, if we move over, or if we make our circle larger, then we're going to get different values. We're going to get different values in the density surface. In fact, as your circle becomes larger and larger, in other words, as your kernel, we're going to use that same term. As that kernel gets larger and larger, then the density surface is going to get more and more smooth. Because you can imagine if your kernel was as large as the entire data set, every value would be the same, because it would find the same number of observations in every single one. So if the circle was bigger, the circle was like this big, as it moved around, how many dots are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then everything would be 10, because that circle would always encompass all 10 dots. You have 10s everywhere. So as you increase the size of this circle, your density surface becomes less and less unique, more smooth than.
Would you say it's less accurate too? Are you saying it's got 3 trees in that one square, but really it has 9?
Probably less precise, if you're going to say it. Yeah. because there are 10 trees within maybe that circle was 100 meters wide. There are 10 trees within that area. It's just you probably you made your data very, very fuzzy. All right. There are options in most GIS software packages to actually do kernel density estimation using a kernel like this, where instead of just counting up the numbers, then if you can imagine a normal distribution function like this that is put over every single point, and instead of counting up the raw counts, it counts up the proportion of this pile that's within the circle. So you've got less. Basically, you don't. It's not just in or out of the circle. So the circle may get a little bit of this mathematical function, which is usually a normal distribution function, and so it gets some of that area, or it may get the whole thing. But we're going to add all those piles up to get the value.
Accessibility.
Sorry, that came through really fast. I don't know how you
Turn down the volume a little bit, but
turn down which volume.
your volume.
I think you have to use the TV remote control.
Yeah, it doesn't have volume up and down buttons. It just has one volume button that says volume. That's nice.
Is this a little bit better if I just put the
Oh, that's good.
Yeah, when you first said you couldn't hear me, I put the lapel mic like right on my lapel, so it's too loud. Sorry,
That's good.
shouting at y'all. All right, so the kernel shape is defined by a distance parameter. So just like with here, you specify a distance, and it basically smooths the surface more. If you do that, if you define the circle as a larger circle, you'll get a smoother surface. So narrow kernels produce bumpy surfaces. Wide kernels produce smooth surfaces. Yeah. I mean, both of them are valid maps. What's the difference between the two maps? The input data is exactly the same. Yeah. How big this? Yeah. Why might you use one over the other? Like, let's say these represented crime. What's another label for these type of maps that we use a lot?
Heat map.
Yeah, heat map or a hotspot map, right? Hotspot usually actually has a few different connotations, but a heat map is often what we refer to these as. So these are two heat maps of the same data, right? And let's say these represented crime locations. These represented places where crime happened. That's another countable thing. So they might represent robberies. Okay? These are robberies or burglaries, maybe, because this looks like a residential area. And so, am I telling a different story if I show this top map versus the bottom map? It does look like it's worse. That's one thing. And wait, sorry, go ahead.
Precision. The top map is far more precise.
Right. The top map is. Right. Yeah, so I may want to show the bottom map if I want people to like patrol a general region. Like this top map might give the impression that these crimes are really only occurring in these two really small areas. So yeah, it depends a lot on the audience. So, you know, if you're ever in a position where as the GIS technician or analyst, you were to produce maps like this, you could, it doesn't take long time usually to produce the top map and then produce the bottom map or produce a few maps in between, see which one tells you see which one you think communicates the best story. It's the same data, and you could even put on the bottom, you know, this is the average number of crimes within 1,000 feet of that area or within 200 feet of that area. You can report that. So yeah, if you look at the kernel size, it can tell a different story. So here, you know, is the kernel too small? Typically, if you're only capturing 1 or 2 points in your kernel size, it doesn't really do a whole lot of good because your map still isn't doing what the intended purpose is. Like, what's the whole purpose of this? It's to create a surface where you can examine the pattern that you couldn't see before, right? So if you're only capturing 1 or 2 points, you're only seeing the difference between, oh, there's a few more points there than there is there, but you're not seeing the big picture, right? So there is a sweet spot, because if your search size gets too big, then you're not seeing the pattern anymore either, because everything's the same. So maybe here in this example. So here we're getting close to maybe the search pattern being too large. There's a kernel radius of 150 meters compared to 150 kilometers compared to 16 kilometers. All right, and then here we're looking at a different data set. On the left, we've got kernel density estimation, which we've been talking about up to this point. And on the right, we're doing interpolation. In other words, what we're doing here is taking the values stored in those points and making a continuous surface. So that's what we're going to talk about going forward. So I'm talking about 2 different topics today. They're related. They both result in surfaces, but one results in a surface that is based on counts, and the other one results in a continuous surface based on the data. Actually, I'm going to skip to the next slide here real quick and then come back to the slide. So what we're doing here is, if you can imagine, if you take all these points that exist out in space, and the points represent a value, and if you extrude that value up, like let's say this represents elevation, it's not that hard to visualize. So everywhere, like let's say I took a GPS out and I got a bunch of points and I found out what the elevation was. Now I'm looking at a cross section of that elevation. Looking at a cross section. So I want to find a continuous surface rather than just knowing the value at those points. Well, remember back in math class, well, maybe you didn't do this in math class, but in some maths, you might have come up with a trend surface. Okay? So this line represents a trend surface, but this represents actual elevation values, and we're looking at a cross section. So interpolation would be coming up with values at any unknown location. At any unknown location, you have a bunch of empirical measurements, and the values at the unknown locations are interpolation. Right. Yeah, they're trending through these particular ways. The most common way to do this in like math is to minimize the squared differences to come up with a line that minimizes the squared differences from this trend line. And that actually is one method of interpolation that we'll talk about. But there are others, because sometimes we're interested in following this surface a little bit better. Because usually like in the case of elevation, these actually represent the the actual undulations in the ground. We don't want the trend surface. We want the undulations, right? Okay, now you might have heard this word before, extrapolation. But just like in math class, estimating a point outside of this boundary, outside of this range, isn't good. That's referred to as extrapolation. So when you go run these tools, you might see really weird values. If you input these points right here, it may be that these points out here are totally wrong. Usually they are. There's no way of actually estimating how accurate those points are out in this area. It's extrapolation. So you have to know that if you're going to do a spatial interpolation, you want to keep the center, but not the stuff on the outside. We'll talk about a few ways to actually implement that when we do the demo later. Okay. So that's the difference between interpolation and extrapolation. ArcGIS, when you go to hit one of these tools, your goal is to do interpolation, but if you specify your area well outside the range of point values you have, you'll create some extrapolation. And you want to be careful not to use those values out there because you really have no idea if they're accurate. You need to be within your X and Y range of points. This is a cross section, but imagine looking down on this. So some of these points are coming out toward you. You want to make sure that you're within your range of points and you're creating a surface within that range of points, not outside of that range of points. All right. So some of these interpolation techniques rely on simple linear interpolation. In fact, the triangulated irregular network, what it's doing is it's doing a three-dimensional linear interpolation of your data. So right now this is a two-dimensional, like a cross-section of the data, where it's just connecting all of these points. But imagine if you had points out toward you, and I just connected all of the dots and created a triangular mesh with all those points. Then I could calculate the value at any unknown location just using geometry. So here's two dimensions, right? So I can calculate the value of this surface right here. Well, let's say C was unknown. So that's the example here. If C is unknown, okay, these were all points where I actually sampled the elevation. Can't calculate C. Well, C's value would just be the value of A plus the value of 4, and it's halfway between. So I divide it by 2. So that value at C is 6 feet. And the calculations in 3 dimensions are only slightly more complicated. We're still talking about finding our elevation value on a plane. So linear interpolation is how triangulated irregular networks work. But there are also a lot of other interpolation techniques that rely on nonlinear interpolation. So nonlinear interpolation, this is just kind of like a cartoon view. But imagine again, if I have 3-dimension points, nonlinear interpolation takes into account all of the points around you and looks at their values and uses a different formula to come up with those values in several different ways. So we're going to talk about several different nonlinear interpolation techniques here over the next few slides. So we're estimating these values, but we're not just connecting the lines between them in nonlinear interpolation. Now, some of these are going to produce what we call an exact interpolation method. They're going to pass through the known points, right through the known points. So in other words, the predicted surface has the same value as the measured point anytime it passes through a measured point. So if you're doing an elevation, if you're trying to make an elevation data set, it's good to use an exact interpolator because you measured the value at that location, and that's the value that you want it to be. Okay? There are some other ones, some inexact interpolation methods that don't pass through the original points. One of those is a trend surface. A trend surface, it puts a trend through the data rather than trying to match the exact point. So this is a cartoon version. Interpolated surfaces that are non-exact do not go through all of the original data points. They have their place, particularly like a trend surface is useful, particularly in identifying where things are significantly different than the trend. Right? So let's say we're looking at let's say we were looking at the example with the bay, and I noticed that as I traveled, more toward the ocean, I'm just measuring salinity. I traveled more toward the ocean, the bay became more and more salty, right? That makes sense because there's more interaction with the ocean water, right? So I could make a trend surface of the salinity measurements. If I did that, my trend surface would be rising as I got toward the mouth of the bay, correct? Okay, so I go out there. And then I could look at my original observations and I could compare them to the trend surface. And in places where they were higher or lower, it would tell me how unusual those were. And I could go study why is the salinity so different from the trend in this particular location? What's causing the salinity to be different? Or if it was pollution, what's causing the pollution to be so much higher than the trend? In other words, I could do the same thing even if I didn't have a trend surface, but it wouldn't be as powerful because I wouldn't be able to compare differences that are just due to the natural fact that as we get closer to the ocean, we're going to get salinity values. So of course the salinity is going to be lower, way up close to one of the bayous than it is at the ocean. Okay? But there may be a particular reason why there are a few observations that are higher. Well, let's say this one's just slightly higher than it should be, but it's very close to the ocean. Whereas this one is almost the same value as that one that's close to the ocean. Then I might wonder why is the salinity so high way up here? If I was comparing it to the trend surface, I would be able to see those differences. So that's one reason why you might do an inexact interpolation is using a trend surface. Now, trend surfaces are also what we refer to as global interpolations. Global interpolation algorithms use all of the points to estimate a value at an unsampled location. There are local trend surfaces that we'll talk about, but the trend surfaces I've been discussing so far up to this point are looking at all of the points. More interpolators actually look only at a few of the points at a time. They say, let's look at the nearest 5 or the nearest 10 points. So we still have this concept of a moving window, and we look at a neighborhood of points, and the simplest way might be to average all of these points. So what's the average elevation value within this circle? That's going to be the elevation value for that point. That's a simple way to say it. We could say, instead of using the raw average, we could weight them by distance. That's a very common spatial interpolation algorithm. So the closer points get weighted higher than the further points. And really, that's just a basic mathematical formula. It's the same formula that if you're in a class where one assignment is weighted more than another assignment, it's the exact same formula. Where you assign a weight to each of these before you add them up, and you divide them by the sum of the weights. We'll talk about that here in a bit. we talked about this a little bit. Why were we doing interpolation? Maybe I should have put this up at the front, but basically we can't measure everywhere. There are times nowadays where we have sensors that can give us a nearly continuous elevation surface, and also sometimes a few other variables. But lots of times we only have measurements at specific locations. So, and sometimes we just have missing data. Yesterday I had a friend call me that works for an organization, and they're making maps of they're taking satellite data and they're inferring with the satellite data at depth. But sometimes when the satellite data gets too bright, whether through a sun glint or a really brightly reflected object on the bottom, there's no way to infer depth. So they get these no data patches in their data. Okay? So they have a continuous surface, kind of, but it's missing. It's got unsuitable data. We talked a little bit about one way to overcome this earlier in the course when I said that you could just fill it in using you could just fill it in by using a conditional statement and then a neighborhood operation. Okay, we're looking at the average of everything in this circle. That's okay for small areas, but if you have really large areas, it might be better to weight some of those values differently that are further away. And so you could use spatial interpolation. In other words, you could do a interpolation technique that we'll talk about today, and then do a conditional statement where you say, if it's no data, use the interpolated value. If not, then use the original value, rather than looking at the focal mean, in other words, the mean in a certain area. All right, you could also do it for looking in the past, and if you want to change the cell size. Typically, this is now handled inside of the GIS system. So you can specify that you want to change the cell size, make it smaller. Usually this occurs when you're making it smaller, and it'll actually ask you what you want, how you want to do that. You want to use just the nearest neighbor value, or do you want to average the 5 nearest neighbors or the 6 nearest neighbors? It's still a form of interpolation, but it's not exactly what we're going to talk about today. We've talked about spatial autocorrelation a bit in this course, but all of these principles, interpolation itself, relies on this concept of spatial autocorrelation. I think I'm actually going to come back to this when I get into the Kriging section, because it's a little bit more important there. So let's first talk about the deterministic methods. There's actually a fair bit of methods even inside of ArcGIS. Which one's the best one to use? Sometimes people want to know that. There actually isn't a best interpolation method. So if that's one of the only things that you take out of this lecture, that's important. Is that for your particular problem, oftentimes it's best to choose a few different techniques and see which one is working best in your particular situation. And how do you know which one's the best? Well, oftentimes, if you're not doing Kriging, because if you're doing Kriging, and I'll actually do this for you, but if you're not using Kriging, oftentimes what's best is to oversample. Let's say I want to make a surface of temperature or salinity or any of those variables. I would go out and take 100 samples, but I would only actually use a random sample of 90 of those samples to create my surface. And then, once my surface was created, I would use those other 10 samples to assess the accuracy. I could actually do that a few different times. I could use 90 samples, and then I could use a different set of 90 samples and leave 10 others out. I could do that like maybe 5 times. So I have 5 different surfaces that that each used 90 of my 100 samples, and then I could find the average error that it was off. How off was it? Which one ended up being the best one? So that might be important, because in different situations, if your surface really undulates or if it's really smooth, you're going to have different interpolation methods that are good for your data, and it may be also determined by which one kind of looks the best. In some situations, you need to be able to communicate your results to people, and you need to if one data set looks totally wrong, even though you think it might be fairly accurate, that doesn't always work either. Okay. Each produce different results. That's why they're different. If they all produce the same results, there wouldn't be different interpolation methods. So this is what I was saying. Accuracy is judged by withheld sample points. We can talk about how we'd actually do that once we get into the lab. Okay. So usually we're going to create raster surfaces at the end. However, some of these will produce contour lines as an option. Typically, the workflow is you've got your points, you run them through an interpolation algorithm, and you get a raster surface. Then, if you want contour lines, then you create the contour lines. So here is an example. These should actually probably be reversed. These are my individual points. I'm taking my individual points, and I'm producing contour lines. The reason that these aren't reversed is that these are actually going to follow through and be an example here. This is an original data set, and these points are drawn from this original data set. And these points are drawn from this data set. So now we're going to see how close we can get back to this data set by using those sampled locations. Today in this class, we're not really going to talk about sampling, but I am going to mention that notice how they sampled this area more than they sampled this area out here. Why might that be? And if you're going to do a similar exercise, you might want to pay attention to that, right? Why would they sample this area more than they sampled that area based on that contour map? Yeah, it's flatter over here. If this does represent elevation, which I think it does. It says it's elevation. It's flatter over here than it is over here. And so there's more variability. In order to capture that variability, you need more samples. Right? So sometimes we might refer to this as a stratified sample, where we took some samples. We basically found areas where we needed to take more samples. We still derived random samples in those areas, but then we found areas where we probably didn't need as many samples, and derived less samples in those areas. All right, the simplest interpolation method, sometimes it's referred to as Thiessen polygons, sometimes it's referred to as nearest neighbor. It's the simplest method, and what you're doing is you're assigning the value of the nearest point to every single raster cell in the output grid. So with all these processes, we're going to start with points. We're going to overlay a raster grid, and then we're going to find out what the value should be at every raster grid cell. So if I started out with my points here, I overlay a raster grid, the value of every grid cell is just going to be the closest point. That's Thiessen polygons, or nearest neighbor. Why would you use this? Well, the advantages are that it's pretty easy. I told you before, usually we're talking about making continuous surfaces, but this is actually the only interpolation technique that is somewhat valid for discrete variables. In other words, if I was just trying, like let's say my values represented soil type, which isn't really a continuous surface, I just want to make a guess at what the soil type was everywhere else. Well, it's okay to say it might just be the value that's closest. But this also works for continuous data. The accuracy depends largely on the sampling density. In other words, how close your original points are to each other. One of the big disadvantages is that it doesn't look very good. It looks kind of ugly when you create it. If you use this for elevation, you would have like little stair steps everywhere. If these represent elevation, which they do, the cells here would all have a value of 294, and then right about here, you have a value of 285, right at that location. And as you moved over here, you have a value of 283. So you have stair steps. You can imagine that in 3 dimensions. That's what it would do. So that's Thiessen polygons. So this is one representation of how it's being performed. Okay, so it looks like this is what it looks like when you complete it. So all the raster cells in this box have the same value. All the raster cells in this box have the same value. Here it is using the data that we're going to use for our lab today. Here's a distribution of data points. There's actually a bunch of different values in the point data set that we have to work with today. One of them is the zinc in parts per million. There's a bunch of different metals and their parts per million. But this is how the data looks. These are the samples that were taken of this particular data set. We could show the data categorized instead of, so this is high, medium, high, medium low, and high and low. High, medium, low, and low. So that's just a different representation. I know this is using ArcMap. So I made these slides a couple years ago. Originally, I made them all in ARC. This data's been around for a little while. So originally, I made them all in ArcView a long time ago. All right, so here is the Thiessen zones for this data. You can see what I'm talking about, these stair steps. If you imagine this as a three-dimensional surface, your data would have all the same value, and then it gets to an edge and it has a different value. Okay, next interpolation algorithm that we're going to talk about is trend surface. We mentioned trend surfaces already several times, but we're going to talk about it. So a typical trend surface is a global method. In other words, it considers all of the points at the same time. It's inexact. In other words, it doesn't try to pass through all of the data points. And it can be linear or nonlinear. You can actually make a curvilinear surface through your data. You know, I was talking before. It's a pretty simple mathematical formula for a line, right? Well, if we want to make that pass through a surface, in other words, be a plane, then we have a first order trend surface like this, where we basically just have a different coefficient for how the x is multiplied and how the y is multiplied. But the same basic principle applies in that we're trying to minimize all of these differences from the trend surface to the known points. And you don't actually have to specify or calculate this math. ArcGIS calculates the math for you. But this is what it's doing. If you use a first order trend surface, you are asking it to fit a plane through your data. You can alternatively say, I want a second order trend surface through my data. If you put a second order trend surface through your data, you're asking for one of, this is in 2 dimensions, but imagine it, you could also do it in 3 dimensions. So both your x and your y term would have a squared term as well. And that would create one undulation through your data. If you want to do a third order trend surface, and there's less and less utility for each of these trend surfaces, then your third order trend surface is going to have two undulations in your data. It's going to go up and down in both the x and the y dimension, and so on. Fourth order is going to have four undulations. Typically, you don't go that high, because then you would just choose something like one of the exact interpolators. Typically, you're looking at the overall trend. The reason you're doing a trend surface is you're trying to find the overall trend in your data. So you typically do either a first or second order trend surface. So basically, this relies on a type of math called multiple regression. We're predicting the z-value based on two different dependent variables. The x and the y are both dependent variables. So those of you who have taken a statistics class might recognize that, and might recognize this formula here. We're just trying to predict z based on both x and y. Okay, so here is the realization of the trend surface. So if these were our sample points, this is a trend surface, and this is a third order trend surface. You can see that there's an undulation going this direction. See how it's going this direction? There's an undulation going this direction, and there's an undulation coming up from here. There's three different undulations in that. I don't even know if that's a proper mathematical term, but if it was a first order trend surface, it would just all be going, it'd be trending in one direction, and it would be changing only once in one direction. The second order, it'd be changing twice in two different directions. Third order, it's changing in three different directions, and that's why we have the curved lines in these various places. So here's a first order trend. See how it's only going in one direction. Basically, it's the utility of this is that it tells us, hey, as we get closer to the water, the trend is that the pollutant number 3, which I think is still zinc. Yeah, it is still zinc. The zinc increases as we get closer to water. We can see it as a pattern. It's kind of apparent here, but we've got these other values over here that we can't quite explain. Okay, but this just gives us the overall trend. Here's the second order surface. So it's undulating this way once and this way once. So second order trend surface, and we can see the results of that. Those high values there are close to the bottom. Second order trend surface. Here's third order. You can see that we further have a trough in this direction. Like I said, to me, the utility of doing a fourth or fifth order just keeps going down. At that point, it's better to just switch over, because if you're trying to predict the actual surface, then use a different interpolator besides the trend surface. Trend surface is supposed to tell you about the trend. So I do have a fourth order example here, but it's not as helpful or useful as those other ones. All right, splines. A spline is derived from an old technique where cartographers and also CAD drawers would use actual flexible rulers to make curved lines in their on the paper. So it fits a piecewise polynomial function. In other words, that flexible ruler can be modeled as a little trend surface. And so it basically makes little trend surfaces all throughout your data on only a few points at a time. And you can specify that you want it to be exact or inexact. You want it to pass exactly through the points, or you want it to be to pass more as a local trend surface. So it is a local method because it only calculates, or it it only looks at the points in the neighborhood, right? It's nonlinear, obviously it's using a polynomial function. It typically produces a pretty smooth surface. So it produces typically a very visual pleasing surface. So it's good for cartography. So sometimes they refer to them as thin plate splines. You can adjust the tension of the spline so that it'll go more through the points and produce sharper edges. So this is again this is actually probably a pretty bad cartoon. This is a little bit better one maybe. This is taken from the help from the ESRI help sheet. But think of a spline as it models a thin flexible sheet that you're fitting through all your points, or you're getting close to fitting through all your points. And it produces these, I would say, pretty visual, pleasing, undulating surfaces through your data. It's in contrast to some of the other techniques that will produce, which sometimes produce like sharp edges. So here's a regularized spline with the nearest 12 points. Regularized spline with the nearest 6 points. Notice that the nearest 6 points here is a little bit different than the nearest 12 points. Different values. Nearest 3 points. Would you say it's getting more smooth or less smooth? As we go 12, 6, 3. Yeah, it should be getting less smooth. It's kind of hard to tell, but I would say that too. Here's one where instead of being regularized, it uses a tension model, and this will basically cause that trend surface to be a higher order polynomial. Oh, I only have one example of that. Okay. All right. So so spline is commonly used. I would say that it's most commonly used to create a cartographically pleasing interpolation surface. The next one we're going to talk about, inverse distance weighting, or IDW. It's a local method. It's always exact. In other words, the value at a particular location is the value of that known value. If there's a known value at a particular location, then it uses that known value. So it does have the possibility to be linear because there's an exponential term. We'll look at the formula here in a second. But right now, it's going to be linear or nonlinear. This is the formula that basically assigns a weight. So I'm going to go pixel by pixel. I'm going to find the nearby points. I'm going to define nearby points differently. I'm going to find the nearby points, and then I'm going to assign a weight to every point within the circle, and that value is inversely proportional to its distance. That's why it's called inverse distance. So just like that example I talked about before with test scores, if somebody says this test score is weighted twice as much as that test score, that means we're counting that test twice, and we're counting the other test once, or we're counting that test once, and we're only counting half of that test. They have the same effect mathematically. So here's the formula. Okay, it's not a particularly complex formula. So here, I've given you an English representation of it, but if you think about it, what's happening here? Well, we're taking all of the points within a circle, a search radius, and then we're going to find the distance of each sample point to its target location. That's the D in the term. See the D? The D is the distance. So we're getting the D, the distance from each sample to its target location. Then we're going to weight each sample point according to the inverse of its distance. That's why these are basically the sum of the weights. So when you calculate a weighted average, it's the sum of every observation times its weight divided by the weight, right? Because what's a non-weighted average? Is just the sum of all of the observations divided by the number of observations. Another way to say that is it's the sum of all the observations divided by the weights, which is 1 for everybody, for every single observation. So instead, here we're saying it's the sum of all the observations times their weight divided by sum of all the observations times their weight divided by the sum of the weights. That's how that is. So we're averaging the weighted attribute value. So all we need to do is think a little bit harder about how to calculate these weights. But what it does is it creates a surface like this. Oftentimes, before people really looked at kriging, or before it was really common, before it could be calculated really easily in the GIS system, IDW was often thought of as one of the best techniques. And kriging actually shares a lot of, for accuracy, kriging actually shares a lot of similarities to it. Now, it doesn't produce the visually appealing surface that that the splines do, right? And there's a little bit more jagged edges. Those can be smooth. We could select maybe the nearest 12 points. Okay, they're a little bit smoother, but there's still a little bit of jagged areas. Okay. But if we're actually holding out a few of these values and then checking the accuracy, oftentimes it performs very, very well. So here it is with that zinc data. See, it's not quite as smooth as the spline, but typically it's very accurate. All right. And notice if I go back to the formula here, there is an exponential term right here. This R term, that is referred to as the power. Okay. If the power is, basically if the power is 1, then it's a linear interpolator. So what it's going to do is if it squares the distances before, or cubes the differences, or raises them to the 4th, 5th, 6th, 7th, or 8th power, as it does that, it basically pushes those values further away in terms of their weights. So what it does, if you increase the power, what you're doing is you're weighting nearby points even higher than they would be on a linear scale. So 1 would be linear, and if you go below 1, you're actually pulling back in the points that are further away. Because if you raise something to the 1/2 power, you're taking the square root. Okay? So as you go this way, you're pushing those points further and further out. So your interpolated value is going to go, it's usually going to go down because you're stressing the individual point more. The nearest point more. As you go this way, you're stressing the nearest point more. As you go this way, you're stressing the nearest point less. You're averaging the other points more.
So it'll be smoother more towards the 8. Right?
I mean, sorry, I guess I said that wrong. Yeah. So as you go out here, you're pushing the points away, and you're stressing the closest point higher. That's why it's converging on a number. So the closest point must be 30 in this case. And so as your power raises, you're getting closer and closer to just doing Thiessen polygons, because you're weighting only the closest point. Yeah. So I said it wrong. I mean, right, and then I said it wrong. But yeah, as you go out this way, you're weighting the point that's closest more and more, because what you're doing is you're pushing out those other points. You're basically saying, because it's the inverse distance, so you're saying that the distance is greater and greater. You're raising the distance to the 8th power, or to the 7th power, or the 6th power, and so on. Okay. So here it is, 500 meter fixed with the second, with 2 as the power, and then 100 meter. So you're looking at all the points within 500 meters or all the points within 1,000 meters. Those are the differences there. Okay. So you're averaging more points. So you're going to get a smoother surface. Okay. There's the 3rd power compared to here. That would be those two differences. Which ones? The second power. Second power versus the third power there. The third power looks less smooth because you're using more points. I mean less points. You're weighting the other points out further. All right. In the lab, I have an example of this, but we're going to go ahead and calculate one example together here right now, and then you can also do it in the lab. All right. So sometimes in the lab, people get confused because we're going to have two different numbers here. I've got my R. I'm calling this R because it's R in the formula. Okay, but be careful. R doesn't mean the search radius in this case. It means the power. Okay, see in the notation, it's the power, not the search radius. So we've already decided that for this particular, the center of this cell that's marked in red, that value is gonna that's the point we're trying to give a new value. That represents the center of a cell. Okay, we've already decided that we're only going to include these 3 points because they're the closest 3 points. So how would we calculate that value, or how does ArcGIS calculate that value? How does any GIS that implements the IDW formula calculate that value? Well, first it needs to find the distances. The distances is the D in the term. So we've got 4, 3, and 2. The X values there are the Z with the X in the parentheses. That's the 100, the 1,600. The 160. And the 200. And then, actually that's all we need, right? Those are the 3 values that we need. So the first thing to do is to derive all the weights there. So A has a weight of 1 divided by 4, which is the distance to that weight, squared. It's squared because we're using the power of 2. So we're taking the distance and we're squaring it. If we were to just leave it at 1, then it'd be 1 over 4, and 1 over 3, and 1 over 2. But now it's going to be 1 over 16, and 1 over 9, and 1 over 4. So we're pushing them out a little bit further. If you can imagine if it was 1 over 4 to the 8th, what's 4 to the 8th? It's got to be a really big number. Anyway, you can imagine how big that would be. If this number gets really big, this number gets really, really small. So its weight is hardly anything. So the closest value gets the highest weight, and it's a lot higher weight than any of the other values. So which of these points is weighted the highest? Which one has the largest weight, the highest value for weight? C, right? The weight is 0.25. In other words, the final number that we're going to derive for that red dot is going to be derived. It's going to take 25% of the value of C. All those weights, actually, they don't. We need to do one more thing. It's not exactly 25% here. We need to do one more thing. We need to adjust the weights and scale them so that they range from 0, so that they add up to 1. Okay? So the way that we adjust the weights to add up to 1 is we divide them by the sum of all the weights. So basically what we're doing here, we calculated this term, and we're going to divide them by the sum of all the weights. So this term right here is these guys. So these individual, calculate this value, and this value. And then we're going to divide them by the sum of the weights. So we're adding all the weights up. We divide each one by the sum of the weights. Now each of these weights add up to 1, right? 0.59 plus 0.26 plus 0.15. So in other words, what's going to happen is C is weighted 0.59. It's going to, 59% of the value that's going to be derived for this is going to come from this. 26 from that, and 15% from that. So let's look here. Let's just, I'm just going to bring up Excel real quick. because I want to just demonstrate. So our distances are 4, 3, and 2 to each of those points. So we could say equals this times this. That's squaring it, right? And then this is going to be 1 divided by that. So we get those values. That's the sum of all those. I'm just going to call that the sum of all the weights. I'm going to say this is equal to this divided by the sum of all the weights. So now we have those numbers. And now we could just take the original values, 100, or the original values, 100, 160, and 200. The final thing to do here is to just multiply each of these values times their weight. And then come up with the sum of all of those values. So that's the interpolated value. Let's make sure that that's the value that we're getting here. Yep, 1.7. Mine's rounded slightly. Okay, but let's look here. What if we change these values to A1? Okay, what would we expect to have happen here? I'm gonna make all of these 3 times. So I cubed these instead of squaring them. And what happened to the number? It got bigger or smaller? It got bigger. Okay. Why did it get bigger? It's because we weighted this one more. So if I go all the way out, let's see if I have, is there a power? Yeah. Results of a number raised to the power. This to the 8th. Oops. Yeah. We're converging on the closest value, just like that graph. So the higher that value, the less smooth your surface will be, the higher this value will be. And if we go the other direction, 0.5, we made the weight 0.5. Now we're all the way down to 159 because we pushed these values out further. We made them closer. We made them more similar in terms of their weight. Yeah, see what effect it has on the weights here. These 3 weights are more similar than if we turn that back to 2. These weights are more different. 16, 9, and 4. Sorry, these weights are more different. So that's how inverse distance weighting works. It takes the values and weights the closer values higher. Another way to say that is it weights the further values less. It's inverse to the distance. But that exponential term makes it nonlinear and can push those values out further. Okay, just to let you know, sometimes it's not like mathematical wizardry here or anything, but you can alternatively, some people prefer one over the other. You can take the original values and multiply them by the raw weights and then add those up. But if you do that, what you have to do is add the values up and divide them by the sum of the weights. So at some point you have to divide by the sum of the weights. But mathematically it doesn't matter whether you divide each weight by the sum of the weights or you divide the total after you calculate the weights by the sum of the weights. So this slide just shows you another way to calculate it by hand, but they're both valid ways. They both work the same way. So if you divide each of the individual weights by the sum of the weights, then add those up, you're fine. Or if you, that's on this side. That's on this side. Or if you do it this way, where you multiply by the weights and then divide, you can do that as well, and it'll produce the same number. Some people think of it differently than other people. It's fine, either way works. The way the formula is written is actually closer to this method, right? Because we didn't divide by the sum of the weights until the end. We multiplied everything by the weight first, and then divided by the sum of the weights. So the way the formula is written is actually implemented like this. So these represent the weights flipped. These represent each of the observations. That's the z with the x inside of it. And then this multiplication formula, that's the weight. That's the other part of the term. And then this is the dividing. You add them all up, which is the sum. And then this is the division of the sum of the weights. So the way it's implemented on that slide is exactly like it's shown there. So this is 100 times the weight, the raw weight. And then 200 times the raw weight. And then 160 times its raw weight. You add all those values up, you divide them by the sum of each of the weights. That's the same as this slide. It's slide 74. All right, 3 o'clock. It might be a good time to take a break to make sure that my video is recording. And this is kind of like the second topic. So let's take a 10-minute break and come back at, let's just come back at 5 minutes after the hour. So it's a little bit more than 10-minute break.